When we envision a sauropod, a familiar silhouette comes to mind: a colossal body, pillar-like legs, and a gracefully arcing neck reaching for the highest canopy. This body plan was an evolutionary triumph, dominating terrestrial ecosystems for over 100 million years. But what if one member of this family broke the mold so radically that it challenges our fundamental understanding of sauropod biology? What if it sported a feature so bizarre it seems to defy engineering logic? This is not a hypothetical. It is a paleontological case file waiting to be solved. We are presented with a herbivore that carried what appears to be a double row of spears on its neck. This is the paradox of Amargasaurus kazawi. Now, let's dissect the evidence and solve the case of this bizarre survivor. Our investigation begins in the early Cretaceous period, approximately 125 million years ago, in what is now Patagonia, Argentina. Here, in 1991, paleontologists Jose Bonaparte and Leonardo Salgado unveiled a near-complete skeleton of a new dicraeosaurid sauropod. It was relatively small for its kind, perhaps 10 meters in length, but its size was not the remarkable feature. The astonishment lay in its vertebral column. Let's place the Amargasaurus skeleton alongside a more familiar relative, like Diplodocus, using a simple schematic. We can observe the shared body plan, the long neck and tail, the quadrupedal stance. But running along the neck and anterior torso of Amargasaurus is a feature with no direct parallel in the animal kingdom: a double row of profoundly elongated neural spines. To grasp the full extent of the anomaly, we must first examine the standard blueprint. In this cross-section of a typical sauropod vertebra, we can identify the central body, the centrum, which bears the weight, and a single blade-like projection on top. This is the neural spine. Its primary function is to serve as an anchor point for the powerful ligaments and muscles that support and move the neck. In most sauropods, these spines are robust and relatively short. Now, let's isolate a cervical vertebra from our subject, Amargasaurus. The difference is immediate and dramatic. The neural spine is not a single blade. It is deeply bifurcated, splitting into two thin, rod-like projections that soar upwards. In the mid-neck region, these paired spines reach their maximum length, measuring up to 60 centimeters tall. They form two parallel palisades of bone running from the base of the skull down the neck and transitioning into shorter, single spines over the hips. This anatomical arrangement presents us with a profound biomechanical puzzle. A sauropod's long neck was already a marvel of biological engineering, a delicate balance of strength and lightweight construction, facilitated by a system of internal air sacs. The addition of this elaborate, seemingly fragile scaffolding introduces a host of functional questions that form the core of our investigation. What was its purpose? How did it not shatter under the stresses of daily life? And what evolutionary pressure could possibly select for a feature that seems on its face to be a significant liability? This isn't just an ornament. It is a structural modification that would have governed the animal's entire existence. The bones are our only direct evidence, and they are telling us a story of radical adaptation. Our task is to learn how to read them. To solve the paradox of Amargasaurus, we must move beyond a simple observation of the fossil and conduct a rigorous biomechanical investigation. The central question is one of function and structural integrity. How could such delicate-seeming structures operate on the neck of a multi-ton animal without catastrophic failure? The answer lies encoded within the fine details of the bones themselves. Let's isolate a single pair of these cervical spines for closer inspection. On a digital model, we can rotate them and analyze their form. Unlike the flattened, blade-like neural spines of an animal like Stegosaurus, the spines of Amargasaurus are almost perfectly circular in cross-section. They are, in essence, elongated bony rods. Furthermore, high-resolution scans of the fossil surface reveal fine parallel striations running along their length, a subtle but critical clue we will return to. From an engineering perspective, a long, thin rod is exceptionally vulnerable to bending and buckling forces, especially when loaded from the side. This inherent weakness presents our first major analytical challenge. We can model the forces acting on the neck. As the animal lowers its head to drink or browse on low-lying vegetation, the neck muscles and the massive nuchal ligament, which we know ran in the deep channel between the two rows of spines, would have supported the load. Let's visualize this with an overlay of the primary muscle groups onto the skeleton. The spines provided tall anchor points, potentially giving the muscles greater leverage. However, any significant lateral movement, such as a quick turn of the head to scan for a predator, would introduce immense side-loading stresses. To quantify this, we can use a 3D wireframe model of the cervical vertebrae to simulate the neck's range of motion. Articulating the vertebrae reveals a significant constraint, while vertical flexion, moving the head up and down, was relatively unimpeded. Lateral flexion, side-to-side movement, was severely restricted. Any bend beyond a few degrees would cause the tall, parallel spines to collide with one another. This anatomical reality immediately casts doubt on certain functional hypotheses. The idea of the spines being used as active defensive weapons, swung at a predator, becomes biomechanically untenable. They were too fragile for direct impact, and the neck lacked the necessary flexibility to wield them effectively. With this structural understanding, we can now systematically evaluate the competing theories for what soft tissue, if any, was associated with these spines. The first and simplest hypothesis suggests they were naked spines, covered only by a thin layer of skin. In this model, they would have formed a visually intimidating spiky defense. However, as our analysis showed, they were ill-suited for combat. A predator attacking the neck could have easily snapped these rods, leading to debilitating injury. The bone structure simply does not support a primary defensive role. A second, more popular hypothesis proposes the existence of a skin sail. Let's break this down with a 2D diagram. One version suggests two parallel sails, with a membrane of skin stretching independently along each row of spines. Another version posits a single, broad sail, with skin stretching between the tips of both rows. This structure is often compared to the sail of the Paleosaur Dimetrodon, and is theorized to be for thermoregulation, or, more plausibly, for display. But the biomechanics again present a problem. A single sail would have acted like a kite in the wind, placing enormous stress on the slender bone tips. Furthermore, the deep groove between the spine bases was the known channel for the crucial nuchal ligament system. A sail structure would interfere with this, or be constrained by it. While a double sail is more plausible, the argument for a thin, delicate skin membrane remains weakened by the fragility of the underlying bone. This leads us to the third and most compelling hypothesis, one rooted in comparative anatomy with modern animals. Let's return to those fine striations on the bone surface. This texture is not random. It is a diagnostic feature known as a neurovascular correlate. It indicates the presence of a rich network of blood vessels. In this cross-section of a modern bovid horn, we can see an inner bone core and an outer sheath of keratin. The bone core exhibits the very same type of surface texturing we see on the Amargasaurus spines. This is our smoking gun. the evidence strongly suggests the bony spines were not the final structure, but rather osteocores for enormous keratinous sheaths. Let's overlay this concept onto our model. By adding a thick layer of keratin, the same strong, lightweight material that constitutes bird beaks, claws, and horns, the entire dynamic changes. The diameter of each spine would have been significantly increased, and its structural strength would have multiplied exponentially. The composite structure of bone and keratin would be far more resistant to bending and fracture than bone alone. This solves the core paradox of their apparent fragility. The spines were not delicate rods. They were the foundations for a pair of formidable, horn-like structures. This keratin sheath model aligns perfectly with the osteological evidence and resolves the primary biomechanical objections. The question is no longer how this structure could exist, but why it evolved in the first place. Our biomechanical investigation has resolved the paradox of structural integrity. The striations on the fossilized bone point overwhelmingly to one conclusion. The elongated neural spines of Amargasaurus were not naked bone, but osteocores supporting formidable keratinous sheaths. This transforms our understanding of the animal, from a creature with a fragile, bony lattice on its neck to one bearing two parallel rows of sharp, resilient horns. But solving the how only deepens the mystery of why. What evolutionary advantage did this elaborate and costly apparatus provide? Here, we enter the realm of competing hypotheses, and we must use a form of controversy clarity protocol to weigh the evidence for each. The first and most intuitive hypothesis is defense. A predator like the Carcharodontosaurid pteranodontan, a contemporary of Amargasaurus, would have thought twice before attacking a neck bristling with sharp horns. Let's visualize this interaction. The horns would have provided a powerful passive defense, not by being actively swung, but by creating a hazardous no-go zone around a highly vulnerable area. Any attempt to bite the neck would have resulted in serious injury to the attacker. While plausible, this theory doesn't fully explain the extreme length of the spines. Effective passive defense could have been achieved with shorter, more robust structures. This leads us to the second major hypothesis, intraspecific display. Throughout the animal kingdom, from the antlers of a moose to the feathers of a peacock, evolution frequently favors exaggerated structures for social signaling. These features serve to intimidate rivals or attract mates. In this context, the horns of Amargasaurus would have been a billboard advertising the individual's fitness. Let's overlay a color pattern onto our model, as these sheaths would not have been drab bone, but could have been brightly colored. An individual with longer, stronger, or more vibrant horns might have signaled superior health and genetic quality, gaining preferential access to mates and resources. This hypothesis is compelling because it accounts for the structure's exaggerated nature, a common outcome of sexual selection. A third, more speculative theory suggests the spines supported a fleshy hump or ridge, perhaps for fat or water storage, similar to a bison or a camel. In this model, the deep channel between the two rows of spines would be filled with this tissue. However, the anatomy presents a problem. Bison have a single row of tall, fused spines, perfectly adapted to support a central hump. The deeply bifurcated parallel spines of Amargasaurus are a far less efficient mechanical solution for supporting a singular central mass. While not impossible, the structure seems poorly optimized for this specific function. So, where does the evidence lead us? When we synthesize the biomechanics with evolutionary principles, the most parsimonious verdict emerges. The keratin sheath model is the only one that satisfies the osteological evidence and structural requirements. Of the functional theories, display, augmented by a secondary role in passive defense, provides the most comprehensive explanation. It accounts for the structure's extreme elongation, its anatomical placement, and aligns with well-documented patterns of sexual selection seen across the tree of life. The defensive benefit would have been a potent secondary advantage. We may never know with absolute certainty, as behavior does not fossilize, but the skeleton of Amargasaurus presents a clear case file, and the verdict of science points towards a creature that used its bizarre anatomy to navigate the complex social landscape of its Cretaceous world. The strange case of Amargasaurus reveals a profound truth about evolution. It is not a linear march toward a single, perfect form, but a vibrant, branching exploration of possibilities. Within the successful sauropod blueprint, there was still room for radical, almost flamboyant, experimentation. This one bizarre survivor forces us to rethink the boundaries of its kind, and stands as a testament to the fact that the fossil record is not just a graveyard of the extinct, but an archive of nature's most audacious designs. What is your hypothesis? Do you think the double row of spines was primarily for display or for defense? Leave your analysis in the comments below. And if you want to own a piece of this investigation, the detailed 3D model of the keratin-sheathed vertebra we analyzed is available for our patrons via the link in the description.